So, in the earlier class, we had seen about legendary transformations which was applied to thermodynamic systems. Mixed systems. So the idea was that for an isolated system, I usually have u as a function of SVN, and depending on the experimental situation that we have, we can replace the extensive coordinates by the corresponding intensive coordinates. The conjugate, the generalized force, the conjugate generalized force. For example, if I want to replace entropy by temperature, because T is the conjugate generalized force, then by construction I define Helmholtz free energy F, which is U minus Ts, and this F is a function of Tv and N. And if I want to see how this is a function of Tv and N, we do a dF, and which is du minus Tds minus SDT. Of course, I have the first law, which is TdS is du plus PdV minus mu dN. So all of this discussion that we are having, particularly given this form of the internal energy where it's a function of V and N, implies that we are talking about a hydrostatic system. So in principle, you can carry out the same argument by writing U as a function of x1, x2, xn, where this is now applicable for any general thermodynamic system you're talking about. This one alternatively can be written down as TdS minus PdV plus mu dN. We shall require both of this, and one can clearly eliminate du minus TdS from this to write down this as SDT minus PdV minus plus mu dN. Let's just check whether this is correct. Du minus TdS is minus PdV plus mu dN. Right. Now you see here it's T, V and N. Therefore this quantity is a function of TVN. So one can do it for the Gibbs free energy also. We did that, which basically we wrote down U minus Ts plus PV, and for both of these the prescription of getting to the Helmholtz free energy or the Gibbs free energy was to use the legendary transformation, which was y minus dy dx times x. And this is therefore was for a single variable. If I want to generalize this, then this would be y minus del y del xi xi. For the enthalpy, we used U plus PV. Here you replace this is a function of T, P and N because you have replaced the volume and the entropy, and this is a function of this has to be H, S, V and N. All of these thermodynamic potentials that we see have their own applications. For example, F is typically conserved. F is conserved if I have, for an isothermal process, with no mechanical work. Which means dV is 0, dt is 0, dN we take it usually to be 0 because it's a closed system, there is no exchange with the particle. This is typically for an isothermal process in presence of a constant force. For example, you are doing the experiment where you have connected the system to a thermostat as well as to a barostat, where the pressure on the system remains constant as well as the temperature remains constant. Then G is conserved. So if you take the system from A to B, then the Gibbs free energy is conserved, it remains the same. And this is typically for an adiabatic process So you have replaced V, I'm sorry, this has to be SPN. You have replaced V by the conjugate force, which is the pressure, adiabatic process in presence of a constant force. So I hope this is clear to you now. I mean, one can keep on deriving this kind of thermodynamic potentials. So one can go further by writing U minus S del S del U minus N del U del N. And this, if I write down, this is going to be U minus Ts, and if you look at the first law, which is over here, then you see that del S del N is minus mu. So this is going to be plus mu, del U del N is plus mu, so that this is going to be minus mu times N. This is what is called the grand potential omega. Look at this. Here you have started off with U, replaced it the entropy by temperature, so T, the volume remains the same, and this is a function of mu. Now recall what you had done for the Euler relation was U is equal to S times del U del S plus V times del U del V plus N times del U del N. So this is the Euler equation which we had studied, because it's a homogeneous, because U is homogeneous of degree 1. Sorry. So therefore this is Ts. What is del U del V? If you are confused about del U del V, look at the first equation. Del U del V is minus P. So this is minus PV plus del U del N is mu N plus mu N. So look at this structure over here, then U minus Ts minus mu N is minus PV. So it follows the omega T, V and mu, which has the exact structure as this, which you have obtained by eliminating the entropy and the particle number, from the functional dependence, is minus P times V. If you define omega by V as small omega, which is now a function of T and mu, because V has been taken care of, then omega T mu is equal to minus P. So this defines the density, and that density must be equal to the negative of the pressure. Once again, this is a function of TVN, and the homogeneity would mean this is lambda F. G is a function of TPN, so only for the, it is homogeneous, so if you want to write G lambda T lambda P N is just going to be G. For the intensive variables, if it's a function of an intensive variable, then it's homogeneous with degree 0 with respect to the internal coordinates. We had H, which was a function of S, P and N. S is the extensive quantity, this means this is lambda times H. It is extensive with respect to only S, therefore it is homogeneous of degree 1 with respect to only S. It is homogeneous of, this is lambda with S and N. It is homogeneous of degree 0 with respect to the intensive coordinate, which is the pressure P. If you want to look at omega, omega is a function of T, V and mu, so lambda V means lambda omega T, V, mu. right? So it's only extensive of with respect to volume, which is an it's only homogeneous of degree 1 with respect to the volume, which is expected, right? So this clearly follows from this. If you choose lambda is equal to 1 by v, then this becomes T mu is, this becomes omega T mu, which is omega over v, and which we have utilized before, and this must be equal to minus of the pressure. So now you clearly know, for the given the experimental situation, I can define the thermodynamic variable which will be relevant. If you look at omega, right, what is omega? Omega, very quickly let's do this, Tv mu is u minus Ts minus mu n. So let's d omega is du minus Tds minus sdt minus mu dn minus md mu. So I have du minus Tds minus mu dn minus sdt minus md mu, and du minus Tds minus mu dn, du minus Tds minus mu dn is minus pdv. So therefore this becomes minus pdv minus sdt minus md mu. Now this one has to be careful in defining. You see, now no longer I have dn but d mu. This is the potential that you use for an open system. An open system is the one which can exchange particles with the environment. So you're allowing, in the Helmholtz free energy F, you are allowing an exchange of temperature, energy with respect to the bath, so that your temperature is kept fixed. In the Gibbs free energy, you are not only allowing an exchange of energy with the bath, but you are also there is also an exchange of mechanical equilibrium, which means the force. The force also has to be same, so that the pressure remains the constant. So you are allowing for the volume fluctuation. In this enthalpy, you are allowing for the volume fluctuation, but your container, clearly they cannot exchange any energy because it's an adiabatic process, or cannot exchange any kind of a heat. In this case, omega, it's an open system where you are allowed to now not only exchange energy, but you are also allowed to exchange the particle number. So in such a system, this is the potential that you use is omega, and in thermodynamics this is called a Grant potential. Isothermal process with no mechanical and chemical work, omega remains a constant, right? So this concludes our discussion on thermodynamic potential. Now what we want to do now here is we want to start off with what is called the Maxwell's relations. And these are a set of relations which are extremely useful in thermodynamics and which you can use to manipulate partial derivatives. So let's start with the first law. So du is Tds minus pdv plus mu dn, right? Now I know that this is a state function. If this is a state function, this means that du is, and this implies that du is del u del s ds plus del u del v dv plus del u del n dn, and therefore you can immediately identify what are these. This corresponds to the temperature, this corresponds to the pressure, this corresponds to the chemical potential. Is this correct? So Tds is equal to du plus p dv minus mu dn, and therefore this is correct. So this means that del u del s is equal to t del u del v is minus p, and del u del n is mu plus mu, right? So now you've identified this derivatives. Okay. Now interestingly, since it's a state function, therefore this is an exact differential. Now if it's an exact differential, that means the mixed derivatives would be equal. So which means that if I want to take pairwise like this, del u del s must be equal to del s of del u del v. When you had taken del u del v, what were the quantities you had to fix? S comma n. Here you had taken s comma v, and here you had taken v comma n, right? So this is del u del s v comma n, and when you take del v of this is s constant. This is del u del v s comma n, and when you finally take a derivative with respect to s, what is it held constant? V is held constant. But del u del s is t, s v comma n is t, therefore this means that del t del v s constant must be del u del v is del p del s volume constant, right? Let's look at this pair now, this and this. If I look at these two pairs, then I have del n of del u del v s comma n. What is held fixed? Volume is held fixed, must be equal to del v of del u del n s comma v. N is held fixed. Am I right? Yeah. But del u del v is minus p, so this means del p del n volume fixed must be del v of del mu del v, n is fixed. Correct? And finally, if I want to take this and look at this, these two terms, so that means what I have, I will write down here, is del n of del u del s v comma n, and then s is equal to del s of del u del n s comma v, n is being held constant. But del u del s is, so this means del t del n entropy is equal to del s of, what is del u del n? Chemical potential, mu in held fixed. So this is the third relation that I get. Now very quickly, so once I have this, please remember that not only here I am holding s as fixed, I have taken a derivative here, so I am fixing s and n, since it's a 3 variable now. Here I am fixing v and n, so this actually has s and v. If I look over here, then when I take this derivative, I am taking the derivative with respect to n, I am holding v and s held fixed, and here n and s held fixed. So v and s, n and s. And finally, when I'm looking at this derivative, I'm not only holding, I'm taking with respect to n, and therefore s and v are held fixed, and this is n and v are held fixed. So please remember this. while you are constructing these relations. Now these relations are consequence of the fact that your internal energy is an exact differential, nothing else. Purely mathematical origin says that my internal energy is an exact differential, therefore it must satisfy the correct criteria that the mixed derivatives must be equal. These relations are called Maxwell's relations. But you see, the problem is that I have derived this relation starting from U. But earlier in a little while ago, we just derived so many thermodynamic potentials, F of, T, V, and N, G of T, P, and N, omega of, first we'll write down H of S, P, and N. And then finally we had omega. What was it function of? We eliminated, so this is T, V, and mu. Clearly all of these are thermodynamic potentials, and we have only looked at one of them. So I can derive all such conditions for each of these potentials. Nobody can stop me, and you are right in doing that also. So in principle, you see, this one has given you 3 Maxwell's relation. So this will give you another 3, this will give you another 3, this will give you another 3, this will give you another 3. 1, 2, 3, 4, 5. So there are 15 Maxwell's relations. The question is, are all of these independent? Which means, are you finding a repetitive Maxwell's relation when you are looking for F, G, H, and omega, which you have already obtained here? So that is the question which we want to understand, or which we are trying to answer here. The straightforward way of doing it is to look at what are called Jacobians. I'm sure you have done Jacobians. Jacobians are very much there when you do coordinate transformation. Right? When you do coordinate transformations, then Jacobians are very, very useful. So if you go from xy to uv, then you essentially do the Jacobian. The Jacobian is written down as this particular way, and is a determinant of del f del x, del f del y, del g del x, del g del y. Right? So here, for example, so here y is held fixed, here x is held fixed, here y is held fixed, here x is held fixed, and if you want to write down explicitly, this is del f del x y constant, del g del y x constant, minus del f del y x constant, del g del x y constant. This is how your Jacobian will look. Clearly it's a determinant. So if you exchange the rows and the columns, you carry over a minus sign, which means if I want to write down del g del f, del x del y, then this is going to be del g del x, del g del y, del f del x, del f del y. I don't want to write what is held constant repeatedly. You should know by now what is. And this, you see, is just done by bringing this over here and this one over here, and therefore this is del of fg by property of determinant is x comma y. Del fg del y del x is again del f del y, del f del x, del g del y, and terribly sorry for this, del g del y del g del x, the determinant of this, and this is going to be minus del of fg del of xy. It's only for two variables, therefore it's very easy to understand, but essentially if you have any even permutation of either the numerator or the denominator, then there is no minus sign. But if there is an odd permutation in rearranging the variables, there is going to be a minus sign. So if you are, for example, del f gh del of x y z is equal to minus of del g f h del of x comma y comma z is equal to del g h f. So if you once again take it over here, then this is going to be like this. So you can clearly understand that you are exchanging the rows twice, and therefore any even permutation should give you a plus sign. Odd permutation should give you a negative sign. Further, del of fg del of xy is 1 over del of xy del of fg, which I can write down del of xy del of f comma g. If you multiply these two, then you will see that you are going to get 1. The most crucial identity that we want to do, del of x comma y u comma v. Let's write down explicitly what this means. Del x f del y f del x g del y g. So my shorthand notation del x f is identical to del f del x, y is being held constant. And here of course I have here I have del ux, del uy, del u, stupid error, del vx, del uy, del vy. Correct? Let's just look at the first term. The first term is this times this plus this times this. So del x f del uy plus del, is this correct? Del yf, I'm sorry, this into this. What am I doing? So this multiplies with this, so that this is del ux, and then I have del yf, del uy. So this is the first term. What do I mean by the first term? Clearly, this matrix is going to be something like this: A11, A12, A21, A22. What I have written down over here is A11. You can write down for A12 and the same A12 and A21 and A22, but this is will suffice for us. This is del f del x, y held constant, del x del u, v held constant, del f del y, x held constant, del y del u, v held constant, and this is del f del u, v held constant. Similarly, if you look at A22, you're going to get del f. So this A11 will be this, del f del u, v constant, del f del v, u constant, del g del u, v constant, del g del v, u constant. This is going to be the product, this combined thing is going to be equal to this determinant. So, but this is nothing but del of f comma g, del of u comma v. So it follows del fg del xy is del xy del uv is equal to del fg del uv, right? If you choose now u is equal to f, v is equal to g, then del fg del xy del xy del fg, I can choose that without any loss of generality, because if the right hand side becomes f and del fg del fg, then this is equal to 1, and therefore I have del of fg del of xy is equal to del xy del fg whole inverse. So this is the one that we were trying to show over here, but we have shown it in a different way, and we have defined or rather we have derived the more general result, which is like this. If you are wondering how we came up with this, so if you are wondering how we came across this, then we have essentially we say del f del x del u plus del f del y sorry del x just a minute. So let's see, we want to see what happens. So del f del x y constant, and then you have del x del u v constant, plus you have del f del y x constant, and then you have del y del u v constant. What we have done was we have written it down as del f del u v constant. If you are wondering how we got this relation, the idea is very simple. So suppose f is a function of x and y, then I know that the total differential is del f del x y constant dx plus del f del y x constant dy. But now I am also told that x is a function of u, y is a function of x is a function of u and v. This is stupid. So I am also told that x is a function of u and v, and y is also a function of u and v. That means dx is del ux du plus del vx dv, and dy is del uy du plus del vy dv. Let's substitute this back over here, over for dx, and this one for dy. If I have that, then I'm going to write down in a very shorthand notation del xf del ux, this multiplies this du plus del xf del vx dv, plus I have del yf del uy du plus del yf del vy dv. If I collect all the terms together, then I have del xf del ux plus del yf del uy times du plus del xf del vx plus del yf del vy times dv. But now if x is a function of u and v and y is a function of u and v, then it follows that f is also a function of u and v. Therefore, I can also alternatively write down that this as del uf du plus del vf dv. And if I compare these two, with this one, then it follows that del f del u v constant is del f del x y constant del x del u v constant plus del f del y x constant del y del u v constant. So of course the second one also follows similarly, and this is the identity that we have used over here to derive this particular relation.